Hello and welcome to this walkthrough on training FinGPT with LoRA and FinGPT. This notebook is based on a Medium article and is a comprehensive guide aimed at beginners diving into the realm of financial large language models films with FinGPT. In this notebook, we will be preparing the data, training the model, and evaluating the results. Let's start with the first code cell, which initializes the working directory and loads a financial sentiment dataset. The first line of code installs the required packages. The second line sets the working directory to the current directory. The third line downloads the financial sentiment dataset from GitHub and saves it in the working directory. The fourth line reads the dataset into a pandas data frame. We will use this dataset to train our FinGPT model. In the first code cell, we are installing the required packages for our project. These packages include datasets, transformers, torch, TQDM, pandas, Hugging Face Hub, SentencePiece, protobuf, CPM kernels, Gradio, and dtextWML, and accelerate. The exclamation mark before the pip command is used to run the command in the terminal. The second line installs the SentencePiece package, which is used for tokenization. The third line installs specific versions of transformers, CPM kernels, and torch. Finally, we install Gradio and dtextWML and accelerate packages which are used for model deployment and optimization. In the second code cell, we are initializing directories. This code block checks if certain paths exist. If they do, it deletes them to avoid data conflicts, and then creates a new directory for the upcoming data. This is done to ensure that the data is clean and there are no conflicts with any previous data. In the third code cell, we are importing necessary libraries and defining some variables. We import the JSON library to work with JSON files, and the pandas library to work with data frames. We define the path to the JSON file and the path to the directory where we will save the data. We also define the maximum number of samples we want to extract from the JSON file. Next, we define a function called processData, which takes in a row from the JSON file and returns a dictionary with the relevant information. This function extracts the question answer and context from the JSON row and returns them in a dictionary. After defining the processData function, we read in the JSON file using the readJSON function from pandas. We then apply the processData function to each row in the data frame using the apply function. This creates a new data frame with the processed data. Finally, we save the processed data frame as a CSV file in the directory we defined earlier. This CSV file will be used for training our model. In the next code cell, we will be loading and preparing the TFNS dataset. We will be using the Hugging Face datasets package to load the dataset and convert it to a pandas data frame. We will also be mapping numerical labels to their corresponding sentiments and adding instructions for each data entry. In the above code cell, we are again loading and preparing the TFNS dataset. We start by importing the necessary libraries from the datasets package. Then we create a dictionary that maps numerical labels to their corresponding sentiments. Next, we load the dataset using the loadDataset function and select the train split. We then convert the dataset to a pandas data frame using the toPandas method. We map the numerical labels to their corresponding sentiments using the apply method and the dictionary we created earlier. We also add an instruction for each data entry using the instruction column. Finally, we convert the pandas data frame back to a Hugging Face dataset object using the dataset from pandas method and assign it to the TFNS variable. We print the TFNS object to confirm that the dataset has been loaded and prepared correctly. In the following code cell, we will concatenate the previously prepared TFNS dataset with the MDB dataset and shuffle the resulting dataset. In the above code cell, We first create a temporary dataset by concatenating the TFNS dataset with itself using the concatenate datasets function from the datasets package. We pass in TFNS2 as the argument to concatenate the dataset with itself twice. This results in a dataset with 19,086 rows. Next, we assign the temporary dataset to the trained dataset variable and print the number of rows in the dataset using the numRows attribute. Finally, we create a new dataset called allDataset by shuffling the trained dataset using the shuffle method with a seed value of 42. We then print the shape of the allDataset to confirm that it has been shuffled correctly. In the following code cell, we will format the dataset for model ingestion. We start by importing the necessary libraries from the transformers package. Next, we define a function called tokenize function that takes in a text input and a label and returns a dictionary with the tokenized input and the label. We use the tokenizer function to tokenize the input text and add special tokens such as CLS and SEP. We also set the maximum length of the tokenized input to 512. We then apply the tokenize function to the allDataset using the map method and assign the resulting dataset to the tokenized dataset variable. We also set the batch size to 16 using the batch size argument. Finally, we print the first entry of the tokenized dataset to confirm that the dataset has been formatted correctly. In the next code cell, we import the JSON library which will be used to load the training data from a JSON file. We also import the TQDM library which provides a progress bar to track the progress of our code. We then load the training data from the JSON file using the JSON load method and assign it to the allData variable. We also print the length of the allData variable to confirm that the data has been loaded correctly. Next, we define a function called prepareTrainValidData that takes in the allData variable and splits it into training and validation datasets. We set the validation dataset size to 0.110% of the data using the trainTestSplit method from the sklearn library. We also print the length of the training and validation datasets to confirm that they have been created correctly. Finally, we call the prepareTrainValidData function and assign the resulting datasets to the trained dataset and valid dataset variables. In this code cell, we have a function called formatExample. This function takes in a dictionary as input and returns another dictionary as output. The input dictionary represents an example problem, and the output dictionary represents the formatted version of that problem. The input dictionary has three keys: instruction, input, and output. The instruction key contains the problem statement, the input key contains the input data for the problem if any, and the output key contains the expected output for the problem. The formatExample function first creates a string called context that contains the problem statement. It does this by using an F string to insert the value of the instruction key into the string. If the input data exists i.e., the input key is not none, the function also adds the input data to the context string. Next, the function appends the string answer to the context string. This is where the expected output will be added later. Finally, the function creates a new dictionary with two keys, context and target. The context key contains the formatted problem statement, and the target key contains the expected output. Overall, this function is useful for formatting example problems in a way that can be easily displayed to users. In this code cell, we have a loop that iterates over each row in a pandas data frame called allDataset. The loop creates a new dictionary for each row and populates it with the values from the instruction, input, and output columns of the data frame. The loop then appends the new dictionary to a list called DataList. This list will be used later to create a dataset that can be used for training a machine learning model. Overall, this code cell is useful for converting a pandas data frame into a list of dictionaries that can be used as input for a machine learning model. In this code cell, we are saving the data list created in the previous cell to a JSONL file. JSONL stands for JSON lines, which is a format for storing JSON objects in a file, where each line represents a single JSON object. The withOpen statement opens a file called dataset.new JSONL in write mode, and the JSON dumps method is used to convert each dictionary and data list to a JSON string. The resulting JSON string is then written to the file using the fWrite method. The TQDM function is used to display a progress bar while the loop is running. The des parameter is used to set the text that is displayed above the progress bar. Overall, this code cell is useful for saving the data in a format that can be easily read by a machine learning model. In this markdown cell, the author is introducing the concept of tokenization. Tokenization is the process of breaking down a piece of text into smaller units called tokens, which can be fed into a machine learning model. This is an important step in natural language processing tasks, as it allows the model to understand the structure of the text and extract meaningful information from it. Now, moving on to the next code cell. In this code cell, we are importing the necessary libraries and defining some variables that will be used later in the code. First, we import the datasets library, which provides a convenient way to load and preprocess datasets for machine learning tasks. We also import the AutoTokenizer and AutoConfig classes from the transformers library, which will be used to load a pre-trained language model and tokenize the input text. Next, we define the model name variable, which specifies the name of the pre-trained language model we want to use. In this case, we are using the Chakotwaminus-6 model from the third deep learning group. We also define the JSONL path variable, which specifies the path to the JSONL file we created in the previous code cell. This file contains the preprocessed data that will be used to train the language model. The save path variable specifies the path where the preprocessed data will be saved after tokenization. This will be used later in the code when we save the tokenized data to disk. Finally, we define the maxSecLength variable, which specifies the maximum length of the input text that will be fed into the language model. If the input text is longer than this value, it will be truncated. The skipOverLength variable specifies whether to skip over long input text or truncate them to the maximum length. In this code cell, we define two functions that will be used to preprocess the data and tokenize it using the pre-trained language model. The first function, preprocess, takes in a tokenizer, a configuration object, an example from the dataset, and a maximum sequence length. It then tokenizes the prompt and target using the tokenizer's encode method. The function then combines the prompt and target IDs into a single sequence, adds the end of sequence token ID to the end of the sequence, and returns a dictionary containing the input IDs and the length of the prompt. The second function, readJSONL, takes in the path to the JSONL file, the maximum sequence length, and a flag indicating whether to skip over long input texts or truncate them to the maximum length. It then opens the JSONL file and reads each line, preprocesses it using the preprocess function, and yields each preprocessed example. If the skipOverLength flag is set to true, the function will skip over any input text that are longer than the maximum sequence length. Otherwise, it will truncate the input text to the maximum length. In the upcoming code cell, the preprocessed dataset will be saved in a PyTorch dataset object and then saved to a file using the torch save function. In this code cell, the preprocessed dataset is saved to a PyTorch dataset object using the FromGenerator method from the datasets module. The FromGenerator method takes a generator function that yields examples from the dataset and creates a dataset object from them. The generator function used here is read_JSONL, which reads examples from a JSONL file and preprocesses them using the preprocess function. The max sec length and skip over length arguments are passed to read_JSONL to control the maximum sequence length and whether to skip or truncate over long input texts. Once the dataset object is created, it is saved to disk using the save to disk method. The save path argument specifies the directory where the dataset will be saved. In the next code cell, the necessary libraries and modules are imported. These include the torch library for PyTorch, the datasets module for creating the dataset, the fine-tune trainer class from the transformers library for training the model, and the Atom optimizer from the torch optim module. The FinGPT model class from the transformers library is also imported, which is the pre-trained GPT-2 model that will be fine-tuned on the dataset. Additionally, the WANDB library is imported for logging the training progress to the weights and biases platform. In the next code cell, the dataset is loaded from disk using the load from disk method from the datasets module. The load path argument specifies the directory where the dataset was saved in the previous code cell. Then, the FinGPT model class is initialized with the pre-trained GPT-2 model and auto tokenizer class from the transformers library. The tokenizer is used to tokenize the input texts and convert them into numerical representations that can be fed into the model. The fine-tune trainer class is also initialized with the model, the training dataset, and the Atom optimizer. The training args dictionary is used to specify the training parameters, such as the number of epochs, the learning rate, and the batch size. Finally, the train method of the fine-tune trainer class is called to start the training process. The WANDB library is used to log the training progress to the weights and biases platform. In this code cell, we are setting up the environment for CUDA to be accessible in the system path. This is specifically for Windows subsystem for Linux WSL. First, we import the OS module which provides a way of using operating system dependent functionality. Then, we set the path environment variable to include the path to the CUDA binary files. We do this by appending /usr/local/CUDA/bin to the current path variable. Finally, we set the LD library path environment variable to include the path to the CUDA library files. We do this by setting it to /usr/lib/wsl/lib/usr/local/CUDA/lib64. This ensures that the necessary CUDA files are accessible in the system path, allowing us to use CUDA for GPU acceleration in our code. In this markdown cell, we are introducing the next section of the code which is related to setting up the training arguments. We will initialize and set the arguments required for training the model. In this code cell, we are importing various modules and classes required for training the model. First, we import list, dict, and optional from the typing module. These are used for type hints in the function signatures. Next, we import Torch, which is the main PyTorch library for tensor computations. We also import Logger from the Loguru module, which is a logging library for Python. Then, we import AutoModel and AutoTokenizer from the Transformers module. These are used for loading pre-trained transformer models and their corresponding tokenizers. We also import training arguments, trainer, and bits and bytes config from the Transformers module. These are used for setting up the training arguments, training the model, and configuring the training process. Next, we import various functions and classes from the PEFT module. These are used for training the model with PEFT performance estimation and fine-tuning, which is a technique for optimizing the performance of transformer models on different hardware platforms. Finally, we import transformers models to LoRA target modules mapping from the PEFT-utils module. This is a mapping between the names of pre-trained transformer models and the names of the target modules in the LoRA low-rank approximation compression algorithm used by PEFT. In this code cell, we are setting up the training arguments for our model. We create a training arguments object and pass various arguments to it. Output dir specifies the directory where the trained model will be saved. Logging steps specifies the number of steps between each logging message. Num train epoch specifies the number of training epochs. Per device train batch size specifies the batch size per GPU. Gradient accumulation step specifies the number of steps to accumulate gradients before updating the model weights. Learning rate specifies the learning rate for the optimizer. Weight decay specifies the weight decay for the optimizer. Warm-up step specifies the number of warm-up steps for the optimizer. Save steps specifies the number of steps between each save of the model. F16 specifies whether to use mixed precision training with float16. Torch compile specifies whether to use torch script to compile the model. Load best model at end specifies whether to load the best model at the end of training. Evaluation strategy specifies when to evaluate the model during training. Remove unused columns specifies whether to remove unused columns from the input data. In this section, we will set up the quantization configuration for our model. This will help us reduce the size of our model without losing significant precision. In this code cell, we are setting up the quantization configuration for our model. We create a bits and bytes config object and pass various arguments to it. Load in 4-bit specifies whether to load the model weights in 4-bit format. FinB 4-bit quant type specifies the quantization type for 4-bit weights. FinB 4-bit use double quant specifies whether to use double quantization for 4-bit weights. FinB 4-bit compute D type specifies the data type to use for computing 4-bit weights. By setting up this configuration, we can reduce the size of our model without losing significant precision. In this section, we will load the base model and tokenizer and prepare the model for in-tate training. Before we proceed, we need to make sure that we have selected the A100 GPU as our runtime. If the code doesn't work, we can try restarting the runtime and running again. In this code cell, we load a different model and tokenizer using the auto tokenizer and auto model classes from the transformers library. The model name is thudum/chackle-6. We also set the trust remote code parameter to true to allow loading the model from a remote source. We specify the device as CUDA to use the GPU for training. Next, we use the prepare model for in-tate training function to prepare the model for in-tate training. However, we get a warning that this function is deprecated and will be removed in a future version. Instead, we should use the prepare model for k-bit training function. In the next code cell, we define the configuration for the LoRA algorithm and set up the necessary components. We also print the number of trainable parameters in the model. In this code cell, we define a function called printTrainableParameters that takes in a model as an argument. This function prints out the number of trainable parameters in the model, as well as the total number of parameters and the percentage of trainable parameters. We first initialize two variables, trainable params and all param, to 0. We then loop through all the named parameters in the model using the named parameters method. For each parameter, we increment all param by the number of elements in the parameter tensor using the numal method. If the parameter requires gradients I, it is trainable. We increment trainable params by the number of elements in the parameter tensor. Finally, we print out the number of trainable parameters, the total number of parameters, and the percentage of trainable parameters. In this code cell, we are implementing the low-rank adaptation LoRA algorithm and setting up the necessary components. First, we define the target modules variable, which is a list of the target modules for which we want to apply the LoRA algorithm. In this case, we are using the transformers models to LoRA target modules mapping dictionary to get the target modules for the Chackle model. Next, we define the LoRA config variable, which is an instance of the LoRA config class. This class defines the configuration for the LoRA algorithm. We set the task type to task type. Causal LM, which means we are using the model for a causal language modeling task. We set inference mode to false, which means we are training the model. We set R to 8, which is the rank of the low rank approximation. We set LoRA dropout to 0.1, which is the dropout rate. We set target modules to the target modules variable we defined earlier. Finally, we set bias to none, which means we are not using bias in the LoRA algorithm. We then call the getPathModel function to get the model with the LoRA algorithm applied. This function takes in the original model and the LoRA config as arguments and returns the model with the LoRA algorithm applied. Finally, we call the print trainable parameters function we defined earlier to print out the number of trainable parameters in the model, the total number of parameters, and the percentage of trainable parameters. In this case, we get a total of 3,390,261,248 parameters, out of which only 1,949,696 are trainable, which is about 0.575% of the total parameters. In this code cell, we are checking if we need to resume training from a previously saved checkpoint. We first define the resume from checkpoint variable, which is set to none. If we want to resume training from a checkpoint, we can set this variable to the path of the checkpoint. We then check if resume from checkpoint is not none. If it is not none, we proceed to load the checkpoint. We first check if the PyTorch model bin file exists in the checkpoint directory. If it does not exist, we check if the adapter model bin file exists. If neither file exists, we set resume from checkpoint to false. If the PyTorch model bin file exists, we load the weights from the checkpoint using the torch load function and store them in the adapter's weights variable. We then call the setPathModel stateDict function to set the state dictionary of the model to the adapter's weights. If the adapter model bin file exists, we follow the same process as above but with the adapter model bin file instead. If neither file exists, we log a message saying that the checkpoint was not found. In this code cell, we are printing the number of trainable parameters in our model using the print trainable parameters method of our model object. The output shows that we have 1,949,696 trainable parameters out of a total of 6,245,533,696 parameters in our model. This means that only a small fraction of the parameters in our model are trainable. The last number in the output, trainable %, represents the percentage of trainable parameters in our model. In this case, it is approximately 0.3%. In this markdown cell, the author is introducing the fourth part of the notebook, which is about loading data and training the FinGPT model. The author provides a stepwise breakdown of the script that will be used in this part. The first step is to load the pre-processed data. The author also mentions that to train the model on Google Colab, one needs to purchase a GPU plan such as Kala Pro or buy 100 compute units for $10. In this code cell, we are loading the pre-processed data using the load from disk method from the datasets library. The data is loaded from the directory /data/dataset_new. After loading the data, we are splitting it into training and testing sets using the train test split method. The first argument of this method is the fraction of data to be used for testing, which is set to 0.2 in this case. The shuffle parameter is set to true to shuffle the data before splitting, and the C parameter is set to 42 to ensure that the same split is obtained every time the code is run. Note that the dataset variable is reassigned to the output of the train test split method, which contains both the training and testing sets. In this markdown cell, the author is introducing the second step of the fourth part of the notebook, which is about training configuration and launch. The author provides a stepwise breakdown of the script that will be used in this part. The first step is to customize the trainer class for specific loss computation, prediction step, and model saving methods. The second step is to define a data collator function to process batches of data during training. The third step is to set up TensorBoard for logging, instantiate the modified trainer, and begin training. In this code cell, the author defines a modified trainer class that inherits from the trainer class provided by the transformers library. The modified trainer class overrides three methods of the trainer class: compute loss, prediction step, and save model. The compute loss method takes in the model inputs and return outputs parameters and returns the loss of the model. The prediction step method takes in the model inputs, prediction loss only, and ignore keys parameters and returns the loss of the model. The save model method takes in the output dir and internal call parameters and saves the model to the specified directory. The data collator function takes in a list of features and returns a dictionary containing the input IDs and labels tensors. The function first sorts the features list by the length of the input IDs tensor in descending order. It then pads the input IDs and labels tensors with the tokenizer pad token ID to ensure that they have the same length. Finally, it stacks the input IDs and labels tensors into a single dictionary and returns it. These methods and function will be used in the next code cell to train the model. In this code cell, the author imports two modules: Summary Writer from the Torch Utils TensorBoard package and TensorBoard callback from the Transformers Integrations package. The Summary Writer module is used to write events and data to a TensorBoard log file. TensorBoard is a visualization tool provided by TensorFlow that allows you to visualize and monitor the training process of your machine learning models. The TensorBoard callback module is a callback function that can be passed to the modified trainer class in the next code cell. This callback function logs the training and evaluation metrics to the TensorBoard log file using the Summary Writer module. In this code cell, the author trains the model using the modified trainer class defined in the previous code cell. First, the author creates a Summary Writer object to write events and data to a TensorBoard log file. Then, the author creates an instance of the modified trainer class and passes in the following parameters. Model, the pre-trained GPT-2 model args, the training arguments, including the number of epochs, learning rate, and batch size trained dataset, the training dataset eval dataset, the evaluation dataset data collator, the data collator function defined in the previous code cell callbacks, a list of callback functions to be called during training, including the TensorBoard callback function defined in the previous code cell. After creating the trainer object, the author calls the train method to train the model. The training process will take some time to complete. Once the training is complete, the author saves the train model to the specified output directory using the save pretrained method of the model object. Finally, the author closes the Summary Writer object. In this code cell, the author saves the train model to the specified output directory using the save_per_train method of the model object. The author also prints the size of the saved model using the OS_path getSize function. This code block allows the user to save and download their train model and check its size. In this code cell, the author is creating a zip file of the saved model directory using the zip command. The at the beginning of the command indicates that it is a shell command, not a Python command. The zip command takes two arguments. The first argument specifies the name and location of the output zip file, and the second argument specifies the directory to be zipped. In this case, the author is zipping the training args output dir directory, which contains the saved model and other related files. After running the command, the output shows the files being added to the zip file and their compression percentage. This code block allows the user to easily download and share their train model as a single zip file. In this code cell, the author is using the Files module from the Google Colab library to download the saved model zip file to the local machine. The files download function takes a single argument, which is the path to the file to be downloaded. In this case, the file is located at /content/savedmodelzip. This code block allows the user to easily download the train model as a zip file to their local machine for further use or sharing. In this code cell, the author is using the Drive module from the Google Colab library to mount their Google Drive to the Colab environment. The Drive mount function takes a single argument, which is the path to the directory where the Google Drive will be mounted. In this case, the author is mounting the Google Drive to the /content/drive directory. After running this code block, the user will be prompted to authenticate their Google account and grant permission for Colab to access their Google Drive. Once the authentication is complete, the user can access their Google Drive files directly from the Colab environment. This code block allows the user to easily save the train model to their Google Drive for safekeeping or further use. In this code cell, the author is using the cp command to copy the fine-tuned model directory to their Google Drive. The cp command is a shell command that allows the user to copy files or directories from one location to another. In this case, the author is copying the fine-tuned model directory from the /content directory to the midrive directory in their Google Drive. The R flag is used to copy the directory recursively, which means that all subdirectories and files within the fine-tuned model directory will also be copied. This code block allows the user to easily save the fine-tuned model to their Google Drive for safekeeping or further use. In this code cell, the author is defining a function called getFolderSize that takes a single argument, which is the path to a folder. The function uses the OS module to iterate through all the files in the folder and its subdirectories, and calculates the total size of all the files in the folder in megabytes MB. After defining the function, the author is calling it with the path to the output dir directory of the fine-tuned model, which was specified in a previous code block. The size of the model in MB is then printed to the console using an F string. This code block allows the user to easily check the size of their train model, which can be useful for determining how much storage space it will require. In this markdown cell, the author is providing a summary of the previous code blocks and highlighting the key takeaways. They mention that the model is now trained and saved, and can be downloaded and used for generating financial insights for other tasks in the finance domain. They also mention the use of TensorBoard for visualizing the training dynamics and performance of the model in real time. The author then introduces the next section, which is about inference and benchmarks using FinGPT. They mention that this section will cover how to use the trained model for inference and running benchmarks, and that the training process took about 10 compute units. Let's move on to the next code cell. In this code cell, the author is installing several Python packages using the pip package manager. The packages being installed are transformers == 4.32, a popular library for natural language processing NLP tasks, including pre-trained models for tasks such as text classification and language generation. PEFT == 0.40, a package for estimating the energy consumption of parallel applications. SentencePiece, a package for tokenizing text, often used in NLP tasks. Accelerate, a package for optimizing the performance of PyTorch models on GPUs. Torch, the PyTorch library for building and training neural networks. Datasets, a package for working with large datasets in Python. Bits and Bytes, a package for converting between different units of digital storage. These packages will be used in the following code blocks for inference and benchmarking with the FinGPT model. Let's move on to the next markdown cell. In this markdown cell, the author is giving a brief description of the upcoming code block. The code block will be about loading the FinGPT model. In this code cell, the author is cloning the FinGPT repository from GitHub using the git clone command. The repository contains the FinGPT model that we will be using in the following code blocks. After cloning the repository, the author is appending the path to the cloned repository to the sys path list. This allows us to import modules from the repository in the following code blocks. In this code cell, the author is importing necessary modules and functions for the upcoming code blocks. First, the author is importing AutoModel, AutoTokenizer, and AutoModel for Kazaam from the Transformers library. These modules will be used to load the FinGPT model. Next, the author is importing PEFModel from the PEF library. This module will be used to evaluate the performance of the FinGPT model. Finally, the author is importing benchmark datasets from the FinGPT benchmarks module. These datasets will be used to evaluate the performance of the FinGPT model on various financial tasks. The datasets include test FPB for financial phrasebank, test FICA for financial intent detection, test TFNS for financial news sentiment analysis, and test NWGI for newswire generation. In this code cell, we are installing the PEF package using pip. The symbol at the beginning of the command indicates that it is a shell command, not a Python command. The pip install command is used to install Python packages from the Python package index pyp. The upgrade flag is used to upgrade the package if it is already installed. After running the command, we can see that the package is already installed and its version is 0.40. However, the command also shows that it is collecting the PEF package again and installing version 0.50. The command also shows that the NumPy, packaging, and sudo packages are already installed and their versions meet the requirements for PEFT. Finally, the command shows a warning about the PEF package being installed, which is related to the Colab environment. In this code cell, we are importing the Drive module from the Google Colab library and then calling the mount function to mount the Google Drive to the Colab environment. The mount function takes a single argument, which is the path to the root directory of the Google Drive. In this case, we are using the path /content/drive. The output of the code cell shows that the Google Drive is already mounted and provides a warning that if we want to forcibly remount the drive, we can call the mount function again with the force remount equals true parameter. This code cell is important because it allows us to access files and data stored in our Google Drive from within the Colab environment. In this code cell, we are checking if a specified path exists using the OS module. First, we define the path we want to check as a string variable path to check. In this case, the path is /content/drive/mydrive/finetune model. Then, we use the OS_path_exists function to check if the path exists. If the path exists, the code will print path exists. If the path does not exist, the code will print path does not exist. In this case, the output of the code cell is path exists, which means that the specified path exists in the Google Drive mounted to the Colab environment. This code cell is important because it allows us to check if a specific file or directory exists before attempting to access it in our code. In this code cell, we are loading a pre-trained language model called FinGPT using the auto tokenizer and auto model classes from the transformers library. First, we define the name of the base model as a string variable base model. In this case, the base model is thudum/FinGPT. Next, we define the output directory for our fine-tuned model as a string variable peft model. Then, we use the auto tokenizer from pre-trained function to load the tokenizer for the base model. We pass in the base model variable as the argument and set trust remote code equals true to allow the tokenizer to be loaded from a remote source. After that, we use the auto model from pre-trained function to load the base model itself. We pass in the base model variable as the argument and set trust remote code equals true to allow the model to be loaded from a remote source. We also set load in 8-bit equals true to load the model in 8-bit precision for faster inference and set device map equals auto to automatically select the best device for inference. Next, we create a peft model object from the model and peft model variables using the peft model from pre-trained function. This allows us to load our fine-tuned model on top of the base model. Finally, we set the model variable to evaluation mode using the model eval function. The output of the code cell shows that the checkpoint shards are being loaded, but it does not provide any other information about the success or failure of the model loading process. This code cell is important because it allows us to load a pre-trained language model and fine-tune it on our own data for specific tasks. In this code cell, we are loading our fine-tuned model on top of the pre-trained language model that we loaded in the previous cell. First, we define the name of the base model as a string variable base model. In this case, the base model is thudum/FinGPT. Next, we define the output directory for our fine-tuned model as a string variable peft model. Then, we use the auto tokenizer from pre-trained function to load the tokenizer for the base model. We pass in the base model variable as the argument and set trust remote code equals true to allow the tokenizer to be loaded from a remote source. After that, we use the auto model from pre-trained function to load the base model itself. We pass in the base model variable as the argument and set trust remote code equals true to allow the model to be loaded from a remote source. We also set load in 8-bit equals true to load the model in 8-bit precision for faster inference and set device map equals auto to automatically select the best device for inference. Next, we create a peft model object from the model and peft model variables using the peft model from pre-trained function. This allows us to load our fine-tuned model on top of the base model. Finally, we set the model variable to evaluation mode using the model eval function. The output of the code cell shows that the checkpoint shards are being loaded, but it does not provide any other information about the success or failure of the model loading process. This code cell is important because it allows us to load our fine-tuned model and use it for specific natural language processing tasks. In the upcoming code cell, we will be running benchmarks to evaluate the performance of our fine-tuned model on various natural language processing tasks. In this code cell, we are defining the batch size for our benchmarking process. We set the batch size variable to 8, which means that our model will process 8 samples at a time during the evaluation process. The batch size is an important hyperparameter that can affect the performance of our model. A larger batch size can lead to faster training and evaluation times, but it can also require more memory and may lead to overfitting. On the other hand, a smaller batch size can lead to slower training and evaluation times, but it can also improve generalization and prevent overfitting. In this case, we have chosen a batch size of 8, which is a common choice for fine-tuning large language models like the one we are using. This batch size strikes a balance between training speed and generalization performance. The output of this code cell is empty, as we are only defining a variable and not executing any code. In this code cell, we are running a benchmark on the TFNS, the Financial Narrative Summarization Test Set. This test set consists of 2388 samples, and we are using a batch size of 8, which means that we will process the test set in 299 steps. We are calling the test TFNS function, which takes in our fine-tuned model, tokenizer, and batch size as inputs. This function will run inference on the test set and return various evaluation metrics, including accuracy, phone score, and weighted phone score. The output of this code cell shows the evaluation metrics for our model on the TFNS test set. We can see that our model achieved an accuracy of 0.8555, a macro phone score of 0.8055, a microphone score of 0.8555, and a weighted phone score of 0.8496. These metrics indicate that our model is performing well on this natural language processing task. In this code cell, we are running a benchmark on the FPB Financial Phrase-Bank test set. This test set consists of 12 samples, and we are using a batch size of 8, which means that we will process the test set in 152 steps. We are calling the test FPB function, which takes in our fine-tuned model, tokenizer, and batch size as inputs. This function will run inference on the test set and return various evaluation metrics, including accuracy, phone score, and weighted phone score. The output of this code cell shows the evaluation metrics for our model on the FPB test set. We can see that our model achieved an accuracy of 0.7409, a macro phone score of 0.6551, a microphone score of 0.7409, and a weighted phone score of 0.6936. These metrics indicate that our model is performing reasonably well on this financial sentiment analysis task. In this code cell, we are running a benchmark on the FICA Financial CA test set. This test set consists of 275 samples, and we are using a batch size of 8, which means that we will process the test set in 35 steps. We are calling the test FICA function, which takes in our fine-tuned model, tokenizer, prompt function, and batch size as inputs. This function will run inference on the test set and return various evaluation metrics, including accuracy, phone score, and weighted phone score. The prompt fun parameter is used to provide a prompt to the user for each sample in the test set. In this case, the add instructions function is used to prompt the user to provide a sentiment label for each financial tweet. The output of this code cell shows the evaluation metrics for our model on the FICA test set. We can see that our model achieved an accuracy of 0.48, a macrophone score of 0.4898, a microphone score of 0.48, and weighted phone score of 0.5592. These metrics indicate that our model is not performing as well on this financial CA task compared to the sentiment analysis task. In this code cell, we are running a benchmark on the NWGI Newswire General Information Test Set. This test set consists of 4,047 samples, and we are using a batch size of 8, which means that we will process the test set in 506 steps. We are calling the test NWGI function, which takes in our fine-tuned model, tokenizer, and batch size as inputs. This function will run inference on the test set and return various evaluation metrics, including accuracy, phone score, and weighted phone score. The output of this code cell shows the evaluation metrics for our model on the NWGI test set. We can see that our model achieved an accuracy of 0.52, a macro phone score of 0.50, a micro phone score of 0.52, and a weighted phone score of 0.49. These metrics indicate that our model is performing slightly better on this news classification task compared to the financial task. In this section, the author compares the performance of their FinGPT model with the FinGPT v3.1 model on different datasets. They trained their model on the TFNS dataset, so it is expected that the test results on that dataset would be good. However, their model's zero-shot performance on the FPB and FICA datasets, which were not included in their training set. The results on the NWGI dataset are reasonable, but the model's performance is slightly better on the news classification task compared to the financial task. The author also mentions that the cost-effective approach they used, which includes the low-rank adaptation LoRA method, makes it economical to train and test the FinGPT model. Finally, the author suggests that exploring additional training data and refining the model further could lead to enhanced performance across different financial NLP tasks. So in summary, this tutorial is about comparing the performance of the FinGPT model with the FinGPT v3.1 model on different financial NLP datasets. The author trained their model on the TFNS dataset and tested it on FPB, FICA, and NWGI datasets. However, the model's performance on the NWGI dataset is reasonable, but slightly better on the news classification task compared to the financial task. The author also mentions that the cost-effective approach they used, which includes the low-rank adaptation LoRA method, makes it economical to train and test the FinGPT model. Finally, the author suggests that exploring additional training data and refining the model further could lead to enhanced performance across different financial NLP tasks. In conclusion, this tutorial provides valuable insights into the performance of the FinGPT model on different financial NLP tasks. It also highlights the importance of exploring additional training data and refining the model further to enhance its performance. The cost-effective approach used in this tutorial can be useful for researchers and practitioners who want to train and test their models on large financial datasets.